The neat thing about linear algebra in general is some very seemingly simple concepts can be interpreted in a bunch of different ways and can be shown to represent different ideas or different problems. And that's what I'm going to do in this video. I'm going to explore the null space, or even better, I'm going to explore the relationship if I have some vector or some matrix A times some vector x, and that is equal to the 0 vector. And we, of course, saw in the last few videos that the null space of A is equal to all of the vectors x in Rn. So this will have n components. This would have to be an m by n matrix. If this was an m by a matrix, I would say all of the vectors in Ra. So this number right here has to be the same as that number in order for the matrix vector multiplication to be valid. But the null space of A is all of the vectors in Rn that satisfy this equation, where if I take A and I multiply it times any one of the vectors in the null space, I should get the 0 vector. And this is going to have m components. And we've seen that in previous. This is going to have the 0 vectors. I'll put it this way. The 0 vector is going to be a member of Rm. So that's what our null space is. Let's explore it a little bit. We know already that our matrix can be rewritten like this. We could just write it as a set of column vectors. I could say this right here, that's v1. Then I'm going to have v2. And I have n columns. So this last column right here is going to be v sub n. So I could, if I define my vectors this way, that's the first vector, that's the second vector, then I can rewrite my matrix A. I could say A is equal to just a bunch of column vectors, v1, v2, all the way to vn. And multiplying this matrix times a vector x, so times x, so times x1, x2, all the way to xn, we've seen in the past on the matrix vector product definition video that this can be interpreted as this is actually just comes straight out of the definition. This is the same thing as x1 times vector 1 times the first column plus x2 times the second column times that column all the way to, and you just keep adding them up, all the way to xn, times the nth column. This just comes straight out of our definition of matrix vector products. Now, if we're saying that ax is equal to 0, so if we're saying that ax is equal to 0, we're looking for the solution set to that. If we're looking at the solution set to ax is equal to 0, then that means is equal to the 0 vector. That means that this sum, we're trying to find the solution set of this sum is equaling 0. We want to figure out the x1s, x2s, x3s, all the way to xn's that make this equal the 0 vector. And what are we doing? We're taking linear combinations of our column vectors. And seeing if we can take some linear combination and get it to the 0 vector. Now, this should start ringing bells in your head. This little equation, or this little expression right here, should start ringing bells. This was part of how we defined what linear independence was. We said that if this was the definition of linear independence, or we proved this fell out of the definition of linear independence, that if I have a bunch of vectors v1, v2, all the way to vn, we say that they are linearly independent. There's kind of the non-mathematical way of describing it is, well, I guess this is mathematical as well, is that, look, none of the vectors can be represented as a combination of the other ones. And then we show that that means that the only solution to this equation would be that x1, x2, all of the coefficients on this has to be equal to 0. That this is the only solution. Linear independence means that this is the only solution to this equation right now. If the only way that you get the 0 vector by taking combination of all of these column vectors, if the only way to do that is to have all of these guys equal 0, then you are linearly independent. Likewise, if v1, v2, all the way to vn are linearly independent, then the only solution to this is for these coefficients to be 0. And we saw that in our video on linear independence. Now, if all of these coefficients are 0, what does that mean? That means that our vector x is the 0 vector. Is the 0 vector and only the 0 vector. That's the only solution. So we have something interesting here. If our column vectors are linearly independent, if v1, v2, all the way to vn are linearly independent, then that means that the only solution to ax equals 0, only solution is that x has to be equal to 0 vector. Or put another way, the solution set of this equation, which is really just the null space is all of the x's that satisfy this equation. So that the null space of A has to only contain the 0 vector. So that's an interesting result. If we're linear independent, then the null space of A only contains the 0 vector, which is another way of saying that, let me write this, that well, I already wrote it down, that x1, x2, all of them have to be equal to 0. Now, if I were to multiply this equation out and get it into reduced row echelon form, what does that mean? We saw in a previous video that the null space of A is equal to the null space of the reduced row echelon form of A. And so if the null space of A is 0 because its column vectors are each linear independent, then that means that the null space of the reduced row echelon form of A must also equal the 0 vector. And that means that if I take the reduced row echelon form of A times, well, maybe I'm being a little redundant, the reduced row echelon form of A, and I multiply that times x times, or I want to solve this equation. The only solution right here is x is equal to the 0 vector. And if you think about what that means, that if this is the only solution, that means that this reduced row echelon form has no free variables. It literally would just have to look like this. It would have to look like this. So this is x, x1, x2, all the way to xn. The reduced row echelon form of A, in order for this to have a unique solution, and that unique solution being 0, the reduced echelon form is going to have to look like this. It's going to have to look like this. 1 times x1 plus 0 times all the other ones. So you're going to have just a bunch of, you're going to have n zeros. And then you're going to have 1 times x2 plus zeros times everything else. And those 1s are going to go all the way down the diagonal. So it's going to look like that. And then that is going to be equal to the 0 vector. And this is going to be a square matrix where this has to be n and this has to be n. How do I know that? Because I said that x1, x2, and all of these have to be equal to 0. So if they have to be equal to 0, if I just write them as a system of equations, if I write x1 is equal to 0, x2 is equal to 0, x3 is equal to 0, all the way to xn is equal to 0. This system of equations, if I wrote it as an augmented matrix, remember this is x1 plus 0, plus 0, x2 plus 0. This as an augmented matrix, and we've done this multiple times, it would look like this. 1, you just have a bunch of zeros, n zeros, and then the 1s would just go down the diagonal. And then you'd have n zeros right there. So that's where I'm getting it from. That if we are linearly independent, the null space of A is going to be just the 0 vector. And if the null space of A is just the 0 vector, then the null space of the reduced row echelon form is only the 0 vector. The only solution is all of the x's equal to 0, which means the reduced row echelon form of A has to essentially just be 1s down the diagonal with zeros everywhere else. So anyway, I just wanted to make this, this is kind of a neat byproduct of an interpretation of the null space. Let me write that. So if the null space, let me summarize our results. The null space of A, if it just equals 0, then that means, and you could go both ways, that's true if and only if the column vectors of A are linearly independent. And all of that's only true. This is true if, all of, maybe I was going to do a triangle, but it might turn into a square. If x1, x2, all of these have to be equal 0. This is the only solution. Only solution. And then that implies that the reduced row echelon, and I didn't do it maybe as precisely as I would have liked, but the reduced row echelon form of A is essentially going to be a square n by n matrix. N by n matrix. And by the way, this can only be true if we're dealing with an n by n matrix to begin with. And maybe I'll do that a little bit more precisely in a future video. But then the reduced row echelon form of A is going to have to look like this, just a bunch of ones down the diagonal with zeros everywhere else. And these all imply each other. Now, what if the null space of A contained some other vectors? Well, then we would have to say that the column vectors of A are linearly dependent. And if they're linearly dependent, then we wouldn't have a reduced row echelon form of A that looked like this. You would have something that would have some free variables that allows you to create more solutions there. But anyway, I just wanted to give you this angle on how you can interpret the null space and how it relates to linear independence.